Okay, so let us get started. So in the last class, we spoke about some iterative methods to solve the Laplace equation. We discussed the Jacobi iteration method. Just quickly, we'll go over it. We are trying to compute the head at node I comma j at the m plus 1th iteration. So the m plus 1 refers to the iteration number. The way we compute that is by taking the average of the neighboring four cells I plus 1 comma j, I minus 1 comma j, I comma j plus 1, and I comma j minus 1, the four neighboring cells, right, that are denoted over here. We take the average of those four values from the previous iteration, right? So you will notice that all of those terms in the numerator have got m in the superscript, which refers to the fact that we are taking the values at those four neighboring nodes from the previous iteration and using that to compute the head at the current node, which is I comma j, at the m plus 1th iteration, right? Now you keep repeating this process. You keep going from m equal to 0, which is like the first iteration, first guess, initial guess, and then you keep going forward until between two successive iterations, the error. So the way the error is defined as it is h of I comma j at m plus 1 minus h of I comma j at m, which means at a particular cell, you compute the head at iteration number m plus 1 and then compare it with the number at the mth iteration. Okay, you do this, you take the absolute value of this, and then you find the maximum value out of all the cells inside our domain, right? Now, our domain is divided up into a number of rows and columns, number of cells, right? And each cell has an I comma j, has an ID which goes by I comma j, the number of the column number and the row number and so on. So if the maximum value of this error, if it is less than a certain tolerance, then you stop iterating, which means across all the cells, everywhere the maximum value of this difference between two successive iterations, if it falls below a certain tolerance value, then you consider that the method has converged to the solution and therefore you stop. Right. Now, the tighter the tolerance criteria is, if you make it 10 power minus 2 meters, it may take a certain number of iterations to converge. If you make it 10 power minus 3, it will take even more iterations. If you make it 10 power minus 4, it will take even more iterations and so on. So this is the Jacobi iteration method. Now, the next method, we just briefly started talking about it in the previous class, is the Gauss-Seidel iteration method. Now, you might have already encountered this in some math course that you guys took. But anyway, so let us just quickly go over what this method involves. Okay, so remember what we are trying to do is we are trying to calculate h of I comma j at m plus 1th iteration, and we know that it is the h comma I comma j minus 1 plus h comma I minus 1 comma j. I'm writing this in a particular order for a particular reason. Just watch what happens. Plus h I comma, oh sorry, I plus 1 comma j. H of I plus 1 comma j. These are the four neighboring cells. So the exact same thing that we did in the previous slide. Okay, just go back to the previous slide. See, in the previous slide also, we had the same terms in the numerator. But what we did in the Jacobi iteration method was we used the value from all of those cells. We used the previous iteration's values. Okay, now in the Gauss-Seidel method, we are going to do a slightly different thing. Okay, now let us say, I'm going to draw one of these. The 5-point stencil, I'm just going to draw that. So this is my 5-point stencil. Right, this is I comma j. This is I plus 1 comma j. This is I minus 1 comma j. This is I comma j minus 1, and this is I comma j plus 1. Okay. So, and remember the numbering goes from I equal to 1, 2, 3, 4 all the way to n, and j equal to 1, 2, 3, 4 all the way to m. Right. Now, when I do this computation, I'm not randomly going from any I comma j to another I comma j. I will go in a systematic manner. Okay. First, I will go to I'll start from j equal to 1, and then I'll go through all these cells from I equal to 1 to n. Then I go to the next row, I go to j equal to 2, then I go for all these cells and so on. So when I arrive at this particular random cell I comma j, right, I'm just describing the method. Because I do it in a systematic manner, right? So the way I'll do it is I'll start computing from here and then go from left to right and then go to the next. So I go from top to bottom, from left to right. Left to right, I go from I equal to 1 to 2, 3, 4, all the way to n. So that is for j equal to 1. Then I come to the next row, j equal to 2. Then I go again 1, 2, 3, 4 for I equal to 1, I equal to 2, and so on up to n. Then I go to the next row and so on. So it's a systematic manner of progressing through the grid. So what happens is when I come to cell I comma j, the value at I comma j minus 1 and at I minus 1 comma j, which is, let me mark it over here. So if this is I comma j, this cell to the left of that cell is I minus 1 comma j, and the cell to the top is I comma j minus 1. So this cell is I comma j minus 1, and this cell is I minus 1 comma j, right? So when I arrive at cell number I comma j, I have already gone through and computed the value at I comma j minus 1 and at I minus 1 comma j, right? So therefore what I do is, for these two cells which have already been computed in iteration number m plus 1, I already have an updated value. So I use the updated value. I use these values from the m plus 1th iteration, and these values I still have not come to them, right? When I'm at cell I comma j, I have not yet reached I comma j plus 1. I have not yet reached I plus 1 comma j. So I only have the previous old value. So therefore, in the Gauss-Seidel iteration method, I do the simple operation of using the value in those cells at which an updated value is available. I use it, and where an updated value is not available, I don't use it, right? So therefore, this Gauss-Seidel method, by doing this, what it allows us to do is that, compared to the Jacobi method, now fundamentally Jacobi and Gauss-Seidel are doing the same thing. At every point, you're simply taking the average of the 4 neighboring cells, right? What matters is the way this iteration is set up. Both methods are iterative methods, which means you make an initial guess and then you keep correcting your guess, right? Similar to any process of trying to find out an answer. If you don't know the answer, you make an initial guess, and then once I tell you, hey, your error is so and so, then you change your guess, and then you get closer and closer and closer, and eventually you arrive at the solution, right? So in a similar way, these two methods are also doing the same thing. I make an initial guess, and then that gives me a very large error. Then I improve my guess, then I improve it further, and keep improving until I reach a satisfactory solution. So both these methods are iterative solutions, iterative methods. The difference is the way in which we handle this average of the 5-point stencil. In the Gauss-Seidel method, we simply use the most recently available value for the previous row and the previous column, right? I minus 1 comma j and I comma j minus 1. For these two cells alone, we have more recent value or more latest value that's available, and therefore we make use of that. That's all there is to it. Okay. Any questions on this? No questions? Okay. Okay. What I'll do now is okay, maybe not. I'll wait for a few more minutes, and then I have an Excel file which actually illustrates this in a very simple way. I'll share that Excel file with you also. Okay. All right. So this is the Laplace equation. This is the simplest possible equation, right? It's a steady state equation, and there are no sources and sinks, right? So it was simple: dou square h by dou x square plus dou square h by dou y square equal to 0. That is the equation that we solved just now. Okay. Now the next thing that we're going to do is we're going to move on to the Poisson's equation. Now, I'll not get into all the details of what Poisson's equation is and the historical background of it. I'll just write the equation out, and then you know how to solve it. Okay, so it's dou square h by dou x square plus dou square h by dou y square plus some w by t equal to 0. Right? So now this is the Poisson's equation. It's a variation of the Laplace equation. You just got one additional term included in this. Now, what does this equation represent? Now, this equation represents a two-dimensional confined aquifer, which is at steady state, right? How do you know it's at steady state? The right-hand side is equal to 0, therefore it's at steady state, right? It's a 2D aquifer. Well, that's obvious. Dou square h by dou x square and dou square h by dou y square. There is no z term, so therefore there's only it's a 2D system. But now I have this additional term w, which is some kind of an external source or a sink. Right? Let us imagine that I have some recharge coming into this system. Okay, so let us look at the dimensions of this term over here. So what are the dimensions of transmissivity? Transmissivity has got dimensions of L square t minus 1. Okay, what about this term? This term has got dimensions of L in the numerator and L square in the denominator. So it is L minus L minus 1 in the so this entire term has got a dimension of L minus 1 because I have h in the numerator and x square in the denominator. So this is L divided by L square, so that's L minus 1. This term is also L minus 1. So if this term has to be L minus 1, then W should have units of, oh, I'm sorry. Oh, no, I'm not sorry. This is okay. I got confused with this T and time. Okay, this T is transmissivity. I'm sorry, in case you guys are wondering. W by T, this T is the transmissivity of the aquifer, which has got units of meter square per day or something like that. So that's L square T minus 1. Okay, so this W, in order to be dimensionally homogeneous, this W must have units of LT minus 1. Only then, when I do LT minus 1 divided by L square T minus 1, I'll get L power minus 1, right? So basically, it's some kind of, let's say, external source, which I'm writing in units of meters per day, for example. Okay, so then, now, what you will notice is that the term, the first two terms, these are similar to the Laplace equation, right? So what I have done is I've simply added an additional extra source or a sink term into this equation. And now I'm trying to solve the problem for a steady state confined aquifer, which is homogeneous and isotropic. That's why there's only one T value, and which has got an external source or a sink. Okay, now let us imagine that this external source is recharge, let's say. Okay, so recharge is usually expressed in centimeters per year or inches per year and so on. So that would be LT minus 1, right? That would fit perfectly with our requirements. So if I rewrite this equation, it will be dou square h by dou x square plus dou square h by dou y square equal to minus w by t. Now we already know how to write this left-hand side. This left-hand side, we have simplified it to in difference form, right? H I comma j. Wait a minute, I have to be careful. Okay, so it will be h of I minus 1 comma j plus h of I plus 1 comma j plus h I comma j minus 1 plus h I comma j plus 1 minus 4h I comma j divided by, now we are going to assume that delta x and delta y are equal. So although I have dou x square and dou y square, if delta x and delta y are equal, which means my cell is square in shape, it's not a rectangle, it's a square, then I can just simply replace Instead of having delta x square and delta y square, I just have delta x, the whole thing square. Right? How I arrived at this, we have already spoken about this in the last class, so there's nothing much to say about that. Equal to minus w by t. And w could be, let's say, recharge. Now remember, what are we solving for? We are simply solving for h at I comma j when we do the entire process. So you just have to solve for h at I comma j. So it will be h I comma j equal to, wait a second. Okay, it will be w delta x square by t. Yeah, it will have a positive sign by 4t, I guess, plus all of these h values divided by 4. Right, I'm not writing the numerator. It's I minus 1, I plus 1, j minus 1, j plus 1, all of those terms in the numerator divided by 4. This is what the equation will look like. Okay, so basically it's not any different from, if you go back to the previous slide, the Gauss-Seidel iteration. What did I have? I had h I comma j equal to the average of the 5-point stencil, I mean the average of the 4 neighbors. Now when I make the equation more complicated, all I have done is to that average, so this is the basically the average of the 4 cells, I have added one more term to it. So it's not very, fundamentally it remains the same. The difficulty level is the same. I have not done anything super duper difficult or anything. It's just it's a fairly simple equation to solve, right? Everybody agrees?
Yes, sir.
Okay, so now you notice that I started off with a simple problem, a steady state confined aquifer, no sources and sinks problem. I have added one level of complexity to this problem. What did I do? I said, let there be an external source or a sink, this W term. Okay. If it's adding water, W will have a positive sign. If it is removing water from the aquifer, it will have a negative sign. That's all. Okay. So all I have done is added one term to the existing equation that we had. And again, you can use, whether you want to use Gauss-Seidel or Jacobi, it doesn't matter. You can still use the same method. All I have to do is add one more term to this, and that gives you the answer to the problem. You're done. Okay. The requirement in terms of other requirements are all going to be the same. You still need 2 boundary conditions in x direction, 2 boundary conditions in y direction. That requirement has not changed, right? Whether I'm solving Laplace equation or Poisson's equation or any other equation for that matter, you still need the boundary conditions. That part is still going to be there. But when it comes down to it, the fundamental equation that we're solving is not very difficult or not very different from what we did in the previous step, right? You've just added one more term and that took care of it, right? Any questions? No questions. Okay. All right. So now let me give a brief background about this Jacobi iteration and Gauss-Seidel method that we just spoke about. Now you can use that for Laplace equation, you can use it for Poisson's equation, you can use it for any of these equations. Generally speaking, between the Jacobi and the Gauss-Seidel, which one do you think will be better? When I say better, I mean which one will get to the answer faster? The method which takes more number of iterations is going to be more expensive, right? If I can solve this problem within 10 iterations, if that is the benchmark, if I can do it in less than 10, is that good or bad? The lesser number
Can
of,
you repeat, sir?
sorry?
Can you repeat?
So let us say if I'm able to solve this using 10 iterations, okay? When I say solve it, I mean until the error becomes less than tolerance. That is the criteria for stopping these iterations. Let us say after 10 iterations, my error has become less than my tolerance. So therefore, I say stopped. Okay. Let us say for the Jacobi method, I'm able to solve it in 10 number of iterations. Now this Gauss-Seidel method, do you think it will take more than 10 iterations or less than 10 iterations, or it will be about the same as 10? What do you think?
It should be same, sir.
It should be same.
Yes.
If it is the same, then why do we have two methods?
I don't know, sir.
Right? If it was the same, then there would be no need for a separate method, right? If it was the same, then it's, well, basically they're not different then. So what happens is, you see Jacobi iteration, there's a philosophical difference in the way we handle the iterations. In the Jacobi method, you use all the old values. When you do the computation for the current iteration, you use all the old values. In the Gauss-Seidel method, out of the 4, 2 are new values, 2 are old values. Which means what? Which means that I'm giving some weightage to the most recent values and some weightage to the old values. I'm not just discarding all the old values and using only new values. I can't do that. I'm not using only the old values and not using the new values. I'm doing a mix of the two, right? I'm 2 of the terms I've got m plus 1 in the superscript, and 2 other terms I've got m in the superscript, which means the more, see, the fundamental understanding is that as you proceed ahead in iterations, you are getting closer to the answer. If that is the case, then Gauss-Seidel method must be getting closer to the answer faster than Jacobi method, right? So, for example, if Jacobi method takes 10 iterations to solve the problem, then Gauss-Seidel may take 8 iterations or 7 iterations, something like that. Okay. Now, we are greedy, right? We always want to do it even faster. So if Jacobi took 10 iterations and Gauss-Seidel took 7 iterations, then I want to do something to make that 7 to 5 or make it 4 or something like that. I want to reduce it even further. Okay. So that is where the next topic that I'm going to discuss. This is this idea of what is called successive over relaxation. Okay. So basically the successive over relaxation works by adopting a weight for computing the hi comma j. Okay. Broadly speaking, our objective is to compute this hi comma j, and to do that, we are going to use this so-called idea of a weighted approach. Okay. So now, before we get into the weight, okay, so we have defined this error. Let's call it E. The error is simply h at I comma j in the m plus 1th iteration minus h of I comma j in the mth iteration. Okay, this is how mathematically we are defining the error. This is error at I comma j. At every cell, you will have a different error, right? So now what I'm going to do is I'm going to define the successive over relaxation factor, or this weight that I spoke about. It's called the SOR factor. Let's call it omega. Now this omega is going to help us solve this this particular problem by using this omega value, which is so-called successive over relaxation factor. Now there's 2 aspects to it. This factor, it has over relaxation, and then there is successive over relaxation. Okay, so there's two words that you have to pay attention to. Successive means you keep repeating it again and again, which is kind of like the iteration, and over relaxation means something is being relaxed. Okay, so let's try to understand what that relaxation is. Okay, so now this over relaxation factor, or this weight, typically lies between 1 and 2, right? When it is equal to 1, there is no relaxation. When it becomes greater than 1, the system is called over relaxed. Okay, and then of course it's supposed to remain less than 2. I mean, I will not get into the mathematics of it, but anyway, so what we do is, our interest is in computing h at I comma j in the m plus 1th iteration. Okay, So now for that, we say that it will be equal to h at I comma j in the mth iteration plus this omega, this over relaxation factors multiplied by this error ei comma j. Right. So now when you look at this equation, it is a little puzzling, because I have defined e at I comma j using h I j at m plus 1. Then how can I use e to compute h I comma j at m plus 1? Doesn't seem like it seems like something is wrong, right? Well, it's not wrong. Okay, we'll work it out. Don't worry. Now let us remember how we defined this h of I comma j m plus 1. Let's just go back a couple of slides. Just look at this. How did we define h of I comma j at m plus 1? How was it defined? It was defined as this. Let us take the simple problem, the Laplace equation itself, for this purposes of this demonstration. You'll just use this equation itself. Okay, I'm going to write this equation again over here. So basically, can I say h equal to this m plus 1 equal to h at I comma j times m plus omega times this e of ij is basically this term minus hij, right? But what is this hij m plus 1? It is h I comma j minus 1 plus h I minus 1 comma j plus h I comma j plus 1 plus h I plus 1 comma j divided by 4 minus h I comma j at m. Now remember, these are all m plus 1, m plus 1. Two of them are m plus 1 term and the remaining two are m terms. Right? So I have not done anything controversial. I have simply replaced this h I comma j at m plus 1 from this method, or the Gauss-Seidel method. The j minus 1 and I minus 1 terms are at time what is that, iteration number m plus 1, and j plus 1 and I plus 1 terms are at iteration number m. The same thing, I've just repeated it over here and replaced it with this, right? So therefore, maybe I'll write this in the next slide. So if I rewrite this, you will notice that there are two terms here, h of I comma j at the mth interval, mth iteration, and this again h I comma j at the mth iteration has got a coefficient of this omega. Okay, I'll just write this in the next equation. So basically, h I comma j at m plus 1 is 1 minus omega times h I comma j at mth iteration. Go back, and then the next term will simply be omega times plus omega times h I comma j minus 1 plus h I minus 1 comma j plus h I comma j plus 1 plus h I plus 1 comma j divided by 4, and these terms are at m plus 1th iteration and these two are at m. So this is basically the successive over relaxation technique. Okay, now remember what I said about omega. Omega value lies between 1 and 2. Okay, so now what will happen to the first term, 1 minus omega? If omega is greater than 1, right, what will happen to it? It will become a negative term. H of I comma j at m will have a negative weightage, and then the next term, which is between 1 and 2, will have this over relaxation. Okay, so therefore, I mean, let's not get into why this method works better than Gauss-Seidel, just the plain Gauss-Seidel. If omega equal to 1, it just becomes Gauss-Seidel method itself, right? If omega equal to 1, what happens to the first term? 1 minus omega. Omega is 1, so 1 minus 1. So the first term goes away to 0. And the second term is simply omega is 1, so you are left with the Gauss-Seidel method itself. So that is the normal Gauss-Seidel method. Now, if I introduce a value of omega greater than 1, then this method becomes over relaxed. Okay, which means it will give negative weightage to the previous iteration and positive weightage to the current iteration, in which there are again two terms. There's 2m plus 1 and 2m values. Okay, so basically and what this does is it actually converges faster than plain Gauss-Seidel. If you do the plain Gauss-Seidel, which is omega equal to 1, if it takes, how much did I say, 7 iterations, then this method may take 5 iterations or 4 iterations, something like that. So basically you're saving some more time. Okay, again, I'm not interested in figuring out why it saves more time. See, we are interested in applying this to solve our own problems. Okay, the mathematicians have figured out the details, and if they say this is better than that, then I believe them. Okay, the why of it is not, I mean, first of all, it's not in the scope of this course, and it is not an interest it is not of interest to a practical civil engineer who's interested in solving these issues. Okay, but in any case, of course, if you're interested, you can go into this and search it up and read about it. I'll leave that as an exercise for you, for those of you who are interested. Okay, so now what I'm going to do is, let me just stop sharing this. I'll share an Excel file. I'll just show you these computations being done for a simple problem. I'll explain the problem statement also. Just hold on. This is not coming up. You're able to see the Excel file? Yes?
Yes, sir.
Okay. So now I'm just showing you this particular problem. Let us say that in this particular problem, I have on all boundaries, this number 10 that is shown is the head in the boundaries. It's a no flow boundary, and the head in the cell, or a prescribed head in all those, sorry, not a no flow boundary, the head in all the boundaries is 10 meters, let's say. Okay, and in the middle of this green 5, that's also given to us. For some reason, in the middle of this domain, there is the head is maintained at 5 meters, and all along the boundaries, the head is maintained at 10 meters. Okay, so the boundary conditions are given. Wherever there's a green cell, I already know the answer. I already know the head. I only don't know the head in these yellow boxes. Wherever I have a yellow box, I don't know the head. Okay, so I make an initial guess of, let's say the head in these yellow boxes is all equal to 8. This is my first guess. Okay, now using this, I'm going to solve this with two methods. One is the Jacobi iteration method. I've set it up in Excel. It's very straightforward. I mean, you can all do it also. So this is the 0th iteration. 0th iteration is my initial guess. For starters, I know that the value is between 10. It must be between 10 and 5, because at one end I have 10 and in the middle I have 5. So naturally, the answer has to be between 10 and 5. It can't be greater than 10, or it can't be less than 5. That's not possible, right? It physically doesn't make sense to that the head in those yellow boxes will be greater than 10 or less than 5. It has to be between 10 and 5, because those are boundary conditions, those are constraints. Okay, so 8 is a reasonable guess to start with. Okay, so then how do I compute this? I'm just going to show you how to do that. So now these are the values after one iteration. How is this iteration calculated? I'll just go to any one cell and show you the formula there. Okay, I hope you are able to see the formula. Look at the formula bar on top. Okay, I can't increase the font size there, but okay, so when I click on this cell, okay, maybe I'll click on this cell. Just look at the formula there. The formula in this cell, now remember, this is the second iteration or the first iteration. So it is going to use, Jacobi iteration will use all the values from the previous iteration. So the 5-point stencil is at work. Okay, what is it doing? It is simply taking the values in these 4 cells, which are its neighbors, right? I minus 1, I plus 1, j minus 1, j plus 1. So the cell to the left, the cell to the right, the cell above, and the cell below. These are the I minus 1, I plus 1, I plus 2, I plus 3, I plus 4, I plus 5, I plus 6, I plus 7, I plus 8, I plus 9, I plus 10, I plus 11, I plus 12, I plus 13, I plus 14, I plus 15, I plus 16, I plus 17, I plus 18, I plus 19, I plus 20, I plus 21, I plus 22, I plus 23, I plus 24, I plus 25, I plus 26, I plus 27, I plus 28, I plus 29, I plus 30, I plus 31, I plus 32, I plus 33, I plus 34, I plus 35, I plus 36, I plus 37, I plus 38, I plus 39, I plus 40, I plus 41, I plus 42, I plus 43, I plus 44, I plus 45, I plus 46, I plus 47, I plus 48, I plus 49, I plus 50, I plus 51, I plus 52, I plus 53, I plus 54, I plus 55, I plus 56, I plus 57, I plus 58, I plus 59, I plus 60, I plus 61, I plus 62, I plus 63, I plus 64, I plus 65, I plus 66, I plus 67, I plus 68, I plus 69, I plus 70 I plus 1 and j minus 1 and j plus 1 respectively, right? So I simply take those values and divide it by 4, add them all up and divide it by 4. When I do that, I get the answer. In this particular cell, it's 8.5. In the next cell, it is 7.25, and so on. So I can simply take that same formula and copy it across. It will just calculate based on all the neighboring cells. It will compute the head in each cell just by taking the average of the 4 neighbors. Okay, I hope this is clear to everybody. If there are any doubts, stop me. You understand what is going on here? Okay, so now the middle cell, which has got a head of 5 meters, that one will not change from iteration to iteration. The boundary cells, which are defined at 10, 10, 10, 10, all of those numbers are 10, those will not change from iteration to iteration. Only the yellow cells, I need to compute this, right? So I've computed after one iteration, then I compute the error also over here. Let me show you the error. How do I compute the error? I simply take the absolute value of the current iteration minus the previous iteration. So it was 9, it says 9 meters here, it was 8 meters there. So the error is 1 meter. Okay, significant error. In some cells, there is the error is larger. In some other cells, the error is smaller in magnitude. Okay, then so out of all of these cells, the maximum error is 1 meter. So this cell is simply telling me the maximum of all of these errors, right? Only when the maximum value of the error falls below my tolerance, I stop iterating, right? You will see that the error is different for different cells. In one cell, it is 1, in another cell, it's 0.5, in another cell, is 0.75. In some other cell, it is 0. Okay, but that's not good enough for me. My error has to be below my tolerance in all the cells. Only then I stop iterating. Okay, so once I have this, then I go to the next iteration. The process is just very mundane and straightforward. Of course, when you look at this, it just keeps evolving with every iteration. Right now in the second iteration, I will use the values from the first iteration, right? So again, I just use the values from the previous iteration and compute the values, and then I again compute the errors in all these cells. It is a very straightforward process. Now you'll notice that in the first iteration, the maximum error was 1. After the second iteration, the maximum error has become 0.38, 3.8 into 10 power minus 1. Already there's been a significant reduction in error, right, in two iterations. Now I go to the third iteration, fourth iteration, and so on, right? So I just go through this process, right? So the error keeps reducing. Error becomes 2.5 into 10 power. See, from 3.8 to 10 power minus 1, it has become 2.5 into 10 power minus 1. And now the next iteration, again it's reduced. From 2.5, it has become 1.8. In the next iteration, now it's slowing down, 1.7, 1.2, 1.1, 7.2 into 10 power minus 2. Okay, keep in mind this is 1.1 into 10 power minus 1. The next iteration has become 7.2 to 10 power minus 2, right? So it has gone down. Next iteration, it goes down even further, 6.5, and then 4.4, and then 4, and then 2.7, and then 2.4, and 1.7, 1.5, 1, and then finally it goes below 1e minus 2. Okay, so if my error tolerance, if the tolerance is 1e minus 2, it takes some 14 or 15 or 16 iterations for the answer to the error to be less than 1e minus 2 in every cell of my domain. Okay, so this is the Jacobi iteration method. So it took around 15 or 16 iterations to reduce by this amount. Okay, now because this approach is so straightforward, I have simply taken Gauss-Seidel iteration also side by side. I start with the same initial guess. Okay, the same initial guess of 8. I started off here, and then I do the same process. Now the only difference is in the Gauss-Seidel method, I will use a combination of the two recent values and the two old values, right? In I minus 1 and j minus 1, I use the recent value. And in I plus 1 and j plus 1, I use the old value, right, of the 5-point stencil. And I move through the entire domain. I keep doing this over the entire domain. Okay. So after one iteration, actually, Gauss-Seidel is worse off than Jacobi. But you will notice that, let me just keep going down. 4.4, 3e minus 1, 1.6, 8.5 e minus 2, 5.2, 3.2, 2e minus 2, 1.4, 9.5 e minus 3, which means, so 9.5, so this is, I think, about 8 or 9 iterations, right? So at the same time, Jacobi was at 4.4 e minus 2, but Gauss-Seidel has managed to uh, decrease the error much faster, right? So Gauss-Seidel method has actually reduced the error much faster. So I think this must have taken 8 iterations or something like that. Okay, number of iterations is definitely lower than the number of iterations that it took the Jacobi iteration method. Okay, and just for comparison, I've also kept the Gauss-Seidel method with the successive over relaxation. So in this case, I have put in this omega successive over relaxation factor 1.2 and tried it. And you can of course play with this. You can try 1.5, you can try 1.6, and you can find out how the answer changes from iteration to iteration and how the convergence can be observed. You can observe how the convergence happens faster and faster, right? So you will notice that in this case, it converges. Yeah, it converges probably in, let's see. Yeah, this takes about 6 or 7 iterations. Gauss-Seidel method took about 9 or 10 iterations. So basically, you have achieved some further 30-40% reduction in the number of iterations it takes to converge. Okay, so that is a pretty big deal, right? So basically, that is what the idea behind this this method is. So now let's go back to our PowerPoint. Okay, just a second. Any questions on this before we move ahead? No questions. Okay. Now, okay, I don't want to bombard you with this ij, I plus 1, I minus 1, and too much today. Are there any questions on the projects? I'm a little concerned that nobody has asked anything or sent me an email, or well, some minor questions came up one day. I hope you guys are making progress on the projects. Any questions on the projects? Understanding, approach. The more silent you are, the more worried I become. Okay, it's due 1 week from today, and I want everybody in the classroom on next Friday. It'll be from 11 to 12. Raish, please check if there's a class after 12 o'clock on Fridays. Is there a class in this room after 12 o'clock? Because in case it goes over, I want to make sure we're not interrupting the next class. Can somebody quickly check if this room has anybody, any class right after this? Usually there's this little piece of paper stuck on the door of the room, which says whether this room is booked for something else or not, some other course. Nobody's speaking. It's very difficult.
Is there. Sir.
Raish, I can't understand what you're saying. Move the microphone a little bit away and then speak slowly.
Okay. Sir, after this class, there is no class.
There is no class. Okay, that's perfect. Very good. So, which means that, in case we still spill over, and go beyond the time a little bit, maybe 10-15 minutes, hopefully not too much. So what I want every team to do is, every team, I'll call out the two teams that have to come and discuss their whatever findings that they have, and they must present their point of view. Usually the first team that will present is the team that is accusing the other team of saying these guys have done something bad or whatever it is, right? So you will first present your results by saying this is our case for why this opponent has messed up whatever, right? Whether it is the pollution or the water level or whatever it is, and then the opponent will come and say no, we are not responsible, it might be something else or whatever it is, right? Depending on what the problem is. Okay, so that's how it will be. First you have the what is called the plaintiff, and then you have the defendant, right? Or whatever. So first you have the prosecution, and then you have the defense, right? So the prosecution will come and try to prove why the opposite side is wrong, and then the opposite side will come and defend and say no, we are not wrong. And then, so 5 minutes each for both teams, and then each team gets a chance to ask the other team basically an interrogation saying, hey, you made this mistake, that mistake, this mistake, you didn't account for this, you didn't account for that, blah blah blah. And then the opposite team has to answer those questions satisfactorily. Okay, and then same thing, and then team 2 can ask team 1, point out the mistakes in their approach, and so on, right? So it will be an interactive session. Now, given that the microphone that we have in the room is not a seems to have some issues, what we can do is, one of the phones can also be connected to the call, but you will have to turn your volume completely down so that only your microphone is working. Okay, so that there's no echo feedback and all of that. So any one of you, if you can turn your phone on but make your volume 0, so that whatever I'm speaking doesn't again come back as feedback through the other microphone. Okay, or you can of course turn off that microphone. Maybe that's well, no, still it'll still create some echo issues. Anyway, so we can work those things out, but it's better to be prepared, well prepared before the day. I don't want us to waste time on the technological issues. Okay, so I think if you guys need help or you have questions, there's only one more week left, so please get this done well and quickly, so that we'll have a good time on Friday, right? It's important, very important, right? It will give a good closure to the whole class, right? Because it brings together all the fundamental concepts that we've discussed, right? Ranging from wells to uh, saltwater intrusion to pollution, velocity, this, that, everything's involved in it. So it requires a synthesis of all the knowledge that you have collected over the entire semester to be able to solve these problems. They're not very difficult. The challenge is in interpreting the results and to interpret the case and to find out what range of values will give you what kinds of results, which will help your case, right? So uh, let me tell you, any side can win the argument. It depends on how well you present your case. Okay, if both sides do a great job, then it's a kind of like a tie. But if one side does better than the other, then there's a chance that anybody can win. I have not made the problems in such a way that it'll always be one side that can win. No, it depends on how well you argue your case. So if you're prepared well, and if you have a strong case, then it will. And you don't have to be polite. I mean, so you have to be polite. I'm sorry. You don't have to be shy of accusing the opposition team. It's a make believe thing. They're not really culprits. You can you can be aggressive, but be polite. Okay. Okay. I misspoke when I said you don't have to be polite. You can be aggressive, but don't be shy of accusing the other team and so on and so forth. Right. So it'll be a good exercise. It'll be a good exercise in learning how to present these kinds of uh, slightly unconventional way of in a classroom setting, right? So I'm hoping it's fun for everybody. Of course, learning happens when you're having fun. So, okay. All right. So if there are no further questions, we will stop now. We will meet again on, I think next Tuesday is Friday timetable. Is that right? I think I saw something like that in the academic calendar. Next Tuesday is Friday timetable, if I'm not mistaken. Okay. So which means we will again have a class at this time. Let me just quickly check the academic calendar. Yes, next Tuesday is Friday timetable. So next November 11th, when we meet, uh, it will be Tuesday time. Sorry, Friday timetable on Tuesday, uh, and then we go from there. Okay. So thank you very much, everybody. Take care. Let us meet on Tuesday at 11 a.m. Friday timetable. Okay. Take care, everybody, and see you all next week. All right. Bye.